So in this video, we're going to start talking about volume rates of flow. So how quickly a fluid will move through some sort of pipe or hose or tubing. So one thing to sort of keep in mind as we talk about in this video and in the next video, that we're talking about ideal fluids. And so an ideal fluid is something that doesn't experience any friction within the pipe. The viscosity or how easily it flows really is negligible. So there's a lot of things that we kind of have to ignore in order for these concepts to remain constant. But when we're talking about things like oil and water, that is very minimal. Like they flow very easily, and therefore it won't really affect the problem. So the equations really apply to those sort of scenarios, even though they're not perfectly ideal fluids. So in this video, we're going to talk specifically about what's called volume rate of flow. So volume rate of flow. So rate, whenever you see that word, it means per unit time. So although the equation's not here, we'll look at it in a second as I go to the Alamo and give you an example. But the volume rate could also be written as volume over time, or V over T. However, there's another equation for it, and I'll derive it on the next slide. But the volume rate of flow can also be calculated by taking the cross-sectional area of the pipe and multiplying by the velocity of the pipe. So if you think about it, when you put your thumb, say, over the edge of a hose, right, it makes the water spray a lot farther. And essentially what you're doing is you are decreasing the area, the opening of the end of the hose, and that will increase the velocity. So if we look at where this equation comes from, here we see volume rate of flow, right? So you've got volume over time. That's the volume rate. And if we look here, if you have this hose as a cylinder, right? So the volume can be calculated by taking the cross-sectional area and multiplying by the change in the length here. So that would give you the volume of the water within the hose. So if instead of volume, I plug in the area times length over time, you can see that while length over time, that's a distance over time measurement, that is velocity. And so it will remain constant from one location to another. So we can set up this equation showing that area times velocity at this location in the pipe is got to be equal to the area times the velocity at this location of the pipe. So since area is decreasing, they're inversely proportional, so that means the velocity must increase. Right. So this gives an example of narrowing the pipe and talks about it in terms of the changing of the radius. So we can look at that in terms of using our equation for the cross-sectional area, where pi r squared gives us this A. And so if we were to cut the radius of the pipe in half, because the radius is squared in the area equation, it would actually cause the velocity to go up 4 times, because you're really 1/4ing the cross-sectional area. So keep in mind that area and velocity are inversely proportional, but so the radius and the velocity would be inversely proportional to the square. Now I'm going to pull up the Alamo and give you sort of a sample problem of what you might see on a classwork other than just a direct proportion like that. So let's look at this, and I'm just going to kind of make it up as I go. So let's say that you have like a kiddie pool, and I'm a horrible artist here, but you've got this little kiddie pool, and let's say that it's just 2 meters across in this direction. And you want to fill it to maybe, let's say, a third of a meter, or like 30 centimeters deep, right? And then over here you have a hose, and it has some opening, and it's spraying water into my pool, right? And notice this is a horizontal projectile. That should be a hint. That could be something that could be calculated with this. And let's say the opening here is about 1 inch, which is 2.54 centimeters, or 0.0254 meters. And let's say that the rate at which the water is leaving the hose, I'm just going to make this up, 3 meters per second is how fast. And I want to know, well, how long would it take to fill my kiddie pool? So how long? How much time? Right? So what we want to look at is there's a volume of water that we want to have over here, right? So I would have the rate of flow over here, and I could set that equal to the volume per unit time. And that would allow me to figure out how much time it would go given that the hose had this cross-sectional area, and that's how fast it was leaving the pipe. Okay. So in order to find the volume of my cylinder here, I just need to use pi r squared times the height of the water, right? And that would give me the volume right here. So I would just do pi times 1 squared for the radius times 0.3, and that would give me my volume. So let's figure out what that is. So pi times 1 times 0.3 gives me about 0.94 is my volume here. And then over here I have area, cross-sectional area times velocity. So again, I've got the radius here, or actually that was the diameter, right? So I'm going to divide that by 2, all right? And then I'll pi r square it, so I've got to square that, and then multiply by pi. Okay, so that gives me my cross-sectional area, and then I would want to multiply that by the velocity that it leaves the pipe, so times 3. So that gives me this over here, this volume rate. I don't know if you can see that, right? So I have this, which is 0.0015, is equal to the volume 0.94, and I'm really trying to find the time that it takes to fill over here. So if I just solve for t, I can just take this and divide by the answer. And I get that it's going to take about 618 seconds. Right? So let's just, so about 10 minutes for me to fill up this kiddie pool with the water that's leaving here, right? So remember that you can use a ratio of this if we're talking about just looking at comparing the relative velocities when we change the size of the opening of the pipe, but we also can use this sort of equation in order to calculate volume rate of flow in this way.